In session 36, we're going to take a look at a more complex rate problem than what we looked at in the previous session. This one's a little bit more complicated to deal with, but by using algebra and using some strategy here in solving this particular problem, we can see that algebra is in fact very helpful in helping us figure out many types of practical problems concerning every day. What we have here is a situation where a pilot must fly a plane 1,200 miles and then must turn around and fly back that same 1,200 miles. On her way there, she flies against a wind of 60 miles an hour, and then on her way back, she's flying with a wind at her back of 60 miles an hour. The trip there took 5 hours, and the trip back only took 3 1/3 hours. What was the speed of the plane before taking the wind into account? Now, before we try to answer that, let me clarify here a little bit. When the wind is flying against her at 60 miles an hour, we are not saying that she's compensating for that by revving the jet's engines stronger and stronger to get back to a speed that she really wants. What we're saying right now is, what was the speed of the plane before taking the wind into account? Let me give you another example. Let's say an airplane pilot is trying to fly at 500 miles an hour, and they know that there's a 50-mile-an-hour wind that's going to be flying against them or blowing against them when they're flying. If they set up their jet to travel at 500 miles an hour in still air with no wind, then that 50-mile-an-hour wind that's blowing against them is going to make them go 50 miles an hour less than the 500 that the plane would have gone in still air, which would mean that the plane is flying 450 miles an hour against the wind. Well, let's say on the return trip, you still have that same 50-mile-an-hour wind, and the plane is being set to travel at a speed of 500 miles an hour, assuming that there was no wind. Well, now that the wind is at the back of the plane, pushing it at 50 miles an hour, it's increasing the speed of 50 miles an hour. So the net speed on the way back is actually 500 plus 50, or 550 miles per hour. That's what this question is asking for when it says, what was the speed of the plane before taking the wind into account? In the previous example I gave you, the speed of the plane without the wind would have been 500 miles an hour. Without there being any wind. But when the wind blew against the plane at 50 miles an hour, it created a net speed of 450 miles an hour, and when the wind blew with the plane, it created a net speed of 550 miles an hour. Okay, let's go ahead now and attack this problem. Once again, distance equals rate times time. Well, what do we know? First of all, we know that our distance is 1,200 miles. So I'm going to go ahead and write that down, 1,200 miles. And what we're going to deal with is the first part of the trip, when she's flying against the wind. Do we know what her rate is in still air, had there been no wind? No. So we're going to assign it the letter R. So R would represent what her rate would be in still air, with no wind blowing either for or against the plane. But in this problem here, the wind is actually blowing against the plane. And it's blowing against the plane at 60 miles an hour. So what that'll do is it'll drag down the speed of the plane 60 miles an hour. So the rate is actually going to be R minus 60. R standing for the rate in still air, minus 60 standing for the rate flying against a 60-mile-an-hour wind. And then we're going to take that and multiply it times our time. Well, what was our time flying there? Our time flying there is 5 hours. Now we can solve this algebraically. We still have our 1,200 here. And now what we're going to do is take our 5 here and multiply it, distribute it through by using the distributive property. And what I'm going to do here from here on in is just drop the units, because it's pretty straightforward what our final unit will be, and that'll speed up the illustration here a little bit. What is 5 times R? We're going to distribute this. 5 times R is 5r. Now what we're going to subtract by using the distributive property, we're now going to subtract 5 times 60. Well, 5 times 60 is 300. So after we've used our distributive property, what we now have on the right-hand side is 5r minus 300. Okay, our r term, r is our variable, is being multiplied by 5, but then from that term is also being subtracted 300. So what we need to do is add 300 to both sides. Well, if I add 300 to the right side, I also have to turn around and add 300 to the left side. Well, what is 1200 plus 300? Here on the left side, it's 1500. On the right-hand side, what is 5r minus 300 plus 300? Well, the minus 300 and plus 300 cancel out to 0. 5r minus 0 is just simply 5r. Now, the last thing that we have to do here to get the r by itself is undo the multiplication, because right now the r is being multiplied by 5. So to undo that multiplication by 5, we need to divide now both sides by 5. And I've run out of room here. So I'm just going to go ahead and rewrite the answer, and we'll do this in our head. What is 1,500 divided by 5? Well, 1,500 divided by 5 is 300. That's the left side of the equation. The right side of the equation is 5r divided by 5. Well, what is 5r divided by 5? Well, it's just simply r, because the 5 divided by the 5 makes a 1, and a 1 times r just leaves us with an r. So we can see here that the rate in still air would have been 300 miles an hour. However, flying against the wind, her net speed is not 300 miles an hour. We have to stick the r value here of 300 back into our formula for our rate. Our rate flying against the wind is actually 300 minus 60. Well, what is 300 minus 60? It's 240. So this is now gone. And if we double checked ourselves, 1,200 does equal 240 times 5. 5 times 240 is 1,200. So what was her net speed in miles per hour flying against the wind on her trip there? Well, her net speed is 240 miles an hour. And she had to fly that way for 5 hours to reach the distance of 1,200 miles. However, her gross speed, her speed in still air would have been 300 miles an hour, with the 60 mile an hour wind then blowing against her, making it 240 miles an hour as the net speed. Now, I'm not going to calculate this out. I'm just going to set it up for you. We can also deal with her return trip. On her return trip, it's still distance equals rate times time, and she's still going the same 1,200 miles. But now her rate on the return trip is going to be the r, which is her rate in still air. For a moment, we're going to ignore the fact that we calculated this out to be 300. At this moment, we're still assuming that that rate is unknown. So that would be r. But since the wind is blowing directly at the back of the plane at 60 miles an hour, it's actually increasing the speed of the plane by 60 miles an hour. So her rate on the way back is going to be r plus 60. R being her rate in still air, and then the 60 miles an hour, her back increasing her speed by 60 miles an hour. And then we're going to take that times our time. Well, what is our time? Our time is 3 1/3 hours. So then at this point, you would distribute this through. You would take the 3 1/3 and you would probably change it to 10/3, the fraction 10/3. You would then distribute that through. You would take 10/3 times 60. You would take 10/3 times r. And then you would solve this equation for r just as we did this one over here. Her net speed then on the way back is how much? Well, r is 300, so her net speed on the way back would have been r plus 60. R is 300. 300 plus 60 would then be 360 miles an hour. So the reason it's so much quicker on the way back is she's going 120 miles an hour more than what she's going on the way there, due to the fact that the wind is blowing with her at 60 instead of blowing against her at 60. Quickly then, as a review, sometimes the exact rate that something is traveling must be written as an algebraic phrase, such as a situation where you're flying against or with the wind. Okay then, that'll wrap up session 36 on some rate problems.